Now I'd like to introduce our presenters for today's discussion, Brian Wright and Jacob Sponsler of Orbitform.
Thank you, Jim. Good afternoon, everybody. Thank you for being here with us today and investing your time at the Assembly Show for our presentation. My name is Brian Wright, Vice President of Sales for Orbitform, and with me is Jake Sponsler, General Manager of Orbitform. And we're here today to share with you a few minutes about who Orbitform is, but primarily dig deep into what is Orbitform's roller forming process. Our objectives today is to share what is roller forming, what's the definition, share with you the two types of roller forming, which are static and articulating, help you determine if roller forming is a viable option for you, for your assembly process, discuss some of the machine options that go along with roller forming with regards to process control and so forth, and then also at the end share with you some typical applications to help make you make a connection with regards to your assembly processes and components and see if there's a relation. So who is Orbitform? Orbitform has been in business since 1984. We are an OEM who is an expert in riveting, forming, fastening, and assembly equipment, design, build, and integration. We're 100% made in the US, located in Jackson, Michigan. 120,000 square foot facility. We're located on 7 acres, so we do have room to grow. We have in-house build team on the floor, electrical assembly, machine build. We have a full staff of design engineers who design in SolidWorks. We have 5 full-time controls engineers with regards to designing our electrical hardware, our programming, and test, trial, and debug of our machines. Roughly 92% of what we manufacture that goes into our products, which is a make versus a buy, other than the commodity components, is made under our roof at Orbitform. We also have a spare parts and tooling team. We have a support staff that goes out from a service standpoint, that does training, maintenance, and operator, as well as the equipment support with our customers. A sales and applications engineering team, purchasing, and a dedicated project management team. We also have one of our biggest assets is our lab, applications lab. We have 3 full-time senior technicians in our lab who are machinists or tool makers by trade. And we get involved working with our customers to do tooling developments and testing. We also do sample processing to determine, one, if the process is viable, which of the processes make sense, which is a good fit, as well as to help determine the capacity of the machines that we're looking at as the equipment solution. What we also get involved in supporting our customers is prototype builds, a lot of small pre-production runs prior to start of production, as well as supporting their validation of their parts. And then finally, we once in a while will get into short production runs. And that's normally when the volumes are very low and it's difficult for our customers to justify capital and tooling purchase for a return on investment. One thing that's nice about Orbitform is we're fortunate to be able to look at every application and take an unbiased approach, because focusing on the functional requirements, oftentimes you can't always be an orbital riveter, can't always be a radial riveter, can't always be roller forming, hot upset, etc. So we focus with our customer to understand what the functional requirements of the joint are, and then work back to determine what's the appropriate process. The processes that we are able to choose from are orbital riveting, radial riveting, impact riveting, flush self-pierce riveting, hot upset forming, and roller forming. So let's dive into what roller forming is.
So before we tell you what roller forming is, let's talk about what it isn't. So here's an example.
Every vote counts.
So that looked really painful. You gotta love Chris Farley. So basically what roller forming is we're using what we call a roller to apply force to the part, and we're forming either a lip or a groove. We do that with what we call rollers. They're generally round, they're precision machined, located in a bearing, located on a bearing, so that when we roll around the part, we're actually spinning freely, so we're not creating a lot of heat or friction on the part. So here are a couple examples of what roller forming is. So crimping here, we have a static roller head coming down and actually forming a crimp over the edge to retain a washer on an engine mount application. Next one's a flaring. So flaring, we're using vertical rollers to come down and actually flare a tube out. And then the final one's grooving. We're using, this is an articulating roller head application, so we'll share more about different types of roller forming in a second, but we're coming in and we're actually forming a groove, an O-ring groove on this part here. So what are the processes that the crimping, flaring, and grooving of roller forming can replace? These are things like press, crimp, and staking, fastening, adhesive, threaded joints, or welding. So when you're considering roller forming, what are a couple of the major considerations that you want to take? You want to start with a joint functional requirement. So are you trying to retain something? How tight do you want to retain that? Do you have a press out force that you're trying to meet? The other thing would be are you trying to form a unique geometry such as a groove? What are the geometric requirements that you need for that groove? The second major consideration would be the type of material. Now we can form multiple materials. We can form steel, aluminum, stainless, brass, a number of other materials. We can also form dissimilar metals together with this process. And then we can also form over delicate materials. So if you think about a good example is we've done applications where we're forming metal over a piece of glass, and we can do that without disrupting the glass. So now that you know what roller forming is and what it can replace, some things to consider for form requirements. Let's discuss why you would want to use it and what the advantages are. So you're going to apply significantly less force into the part because of the way that you're actually rolling or forming the part as opposed to pressing or pushing or displacing material in there. So you end up putting a lot less stress into the part, which creates a less probability of cracking. You're going to contact the part in a 360-degree radius. So a lot of the processes that I talked about where your alternate processes, you're going to form in 3 or 4 spots. With the 360-degree contact, you're going to have a lot larger surface area and a lot stronger retention, a lot tighter joint. And then you're going to have a very controlled process. So it's going to, we're going to be able to form, like I said, more delicately, more controlled. And then it's also a cold forming process. So compared to like welding, you don't have the heat sink problem with part handling. You don't have some of the grain structure problems that you're going to have with welding. And you don't have some of the pack out, some of the heat problems that you have with that. And then also when you're considering it compared to other processes, it's a fairly low cost of capital investment. And also your expectancy of cost after purchase is lower because the longer tooling life, and then also you're not using and consuming a lot of power.
So the two main types of roller forming are static and articulating. Let's first look at static. As you see, the roller head here is mounted to what we call our power head, and the rollers are in a fixed position. The power head provides the rotation and the advanced axial forming force, coming down and forming the lip as we're seeing over, which often replaces a press crimp. The rotation speeds range anywhere from 300 up to 1800 RPM, and again, it's application dependent. The power head can be pneumatic, hydraulic, or servo driven. The finished form height with this process is consistent within plus or minus 1/1000th of an inch. The roller tooling are designed into cartridges which are fixed, and the cartridges are precision ground at assembly, and the taper bearings used allows for less than 1/1000th of play. This type of bearing design increases the bearing life. This roller head design can be either 2 rollers up to 6 rollers in a configuration, but typically most often applications are using 3 rollers. So let's look at articulating roller forming. Again, this roller forming head package is mounted to our standard power head. The big difference with this, similar to like a 3-jaw type chuck, is the rollers are dynamic, forming inward. The power head again provides the rotation, but in this case, it provides primarily the Z-axis positioning of where you want to have that tooling set to form the material. The rotation speeds with this range anywhere from 300 up to 1200 RPM. The power head can be pneumatic, hydraulic, or servo driven. Force to the workpiece is applied radially to achieve the finished form. And again, the consistency of this finished form is plus or minus 1/1000th of an inch. The roller cartridge assemblies are dynamic compared to the fixed. Their bearing support design increases the bearing life as well. Applications in the articulating roller forming is primarily 3 rollers. This process can also be used to form axially, and normally that's when we use our servo power head, where we're coming down. One application comes to mind, slipper valve assemblies, where you have to come down, the power head advances to a position, the roller heads go into the finished form diameter, and then the power head continues with the final form collapse, and then it comes back out and clears. So normally like an undercut, so you can come down, in, and then form again and still get axial, but primarily most of it is radial.
So now that you know about the 2 types of roller forming we offer, let's talk about some of the options that we can offer with that. The first one is process intelligence. So for either type of roller forming, for articulating or static, we can provide a load cell and LVDT on the advance of the power head as well as on the gripping of the articulating motion. So what that does for us is it allows us to verify that for process monitoring, we can verify that the correct parameters were hit in terms of force and distance. For process control, we can actually use those load cell and LVDT to form either to a distance or to a force. So the other thing we can do is we can provide a through spindle pressure pad for either one of our roller forming options, and that through spindle pressure pad could be for part verification, part presence verification, could be for stack up check, it could be for orientation check. We could have a load cell or an LVDT on that through spindle pressure pad. So along with, like I mentioned, pressure pads would be the next option we can offer. We can offer that for both styles. There's 2 specific types of pressure pads we offer. The first one is what I mentioned, it's a through spindle pressure pad. Basically this is a pneumatically driven rod that comes through the center of the power head and applies force to the part. It can either apply just a clamping load or actually a preload to the part. We can mount that with either a load cell or an LVDT. We can just do presence based on having a switch there and saying that it's advanced. And then the second, so if we watch the video here, you can see that pressure pad's coming down, it's applying. You can see the part clamps right at the end, so you can see the preload it's applying to it. The other thing is that rod's anti-rotated, so you can see the part has a flat to it and it has a specific orientation that we need to form it to. So when the end of the pressure pad tooling there is set to match that so that the part can't be loaded in the incorrect orientation. So it's coming down and it's forming that lip over. So the second sort of pressure pad is a spring-mounted mechanical pressure pad. So this isn't going to have the capability of having a load cell or an LVDT or a switch, but what it is it's basically a shaft, a shaft and a spring that's mounted in a bearing pack that's mounted right to the face of the roller head or the power head. So what that does is it allows us to apply a clamping force on the part while the bearing makes it so that the roller head can spin freely with the pressure pad applying force and not spinning. So if you watch the video here, you can see it's coming down, the pressure pad is going to contact the part first and apply a couple 100-pound clamping force. And then the power head's going to continue down until we're in the forming location. The rollers take off, but you can see that the pressure pad stays in the right position. That's important because if the pressure pad didn't, it would scuff the part and it would cause some part issues. So the next sort of option we have is a servo stop control. So basically the way our power head advance works as well as the way the articulating motion works is we have a threaded interface with a stop gear on it. That stop gear gets adjusted on the threads to dictate how far it is going to travel to the hard stop. So by adjusting up on the threads, we can create a longer stroke by adjusting down. What the servo stop does in both situations is we use a servo to adjust where that stop gear position is so that we can do it through the controls rather than having someone have to go over there and adjust the stop position. So if we watch the video here, you can see Todd's adjusting the stroke position. You can see where the arrow is. That's adjusting the stop gear position, and it's shortening the stroke in that situation. The back side of the head has the servo on it that's making that adjustment. Now this is showing the power head stroke, so for both articulating and static roller forming, that would be the power head stroke. But the same sort of methodology, we use that same sort of methodology to change the position of the articulating motion. Now the reason this is important is if you have a process where you want to form to a couple different positions in process, you can on the fly adjust where the stop is going to be. You also, if you want speed of changeover, instead of having to have your maintenance guy go over and change that position manually, relying that they're going to set it up to whatever the readout was before, you can have it built into the program, so just simply by changing the part selection, it's going to go to a different position and form to a different hard stop. And so the final options we have are just basically machine options in terms of the way we stop the rotation of the head. Articulating and static roller heads are generally fairly decent size, decent mass, rotating mass. So in terms of wanting to stop that quickly, if you just left it up to turning the motor off, it's going to coast to a stop. The two options we have are a clutch brake or a VFD, a variable frequency drive. Both of those create a little bit safer machine so that it's going to stop quickly. The clutch brake is going to basically create an instantaneous stop, so it's going to be better in terms of that. But what the VFD does for you is it allows you to control the speed at which you rotate, so we can control the position where we stop. So we can add a proximity switch to the power head and basically sense where that roller head is in rotation, slow down right before that, and then stop. And you'll see it right in this video here. So we're rotating, you'll see it slow down right at the end, and then it hits the switch and it stops. Why that's important is for this application, we wanted to load and unload the part. We didn't want the rollers or the jaws for the rollers to get in the way. Same thing if you're doing an automatic transfer into a station and you need to know where those rollers are and know what orientation that's going to be in. We can apply the VFD so we can sense where we're stopping the head.
So of all of our roller forming applications, we've sort of categorized it into 5 main areas. And I want to go through these 5 right now with you. Again, typical applications that we've been involved in. We're going to first start with end forming. In some of the ones you've already seen before, using a static roller form right here, the roller head, coming down and forming lip, again, often taking place of a press crimp. What's nice, as Jake mentioned earlier, significantly less force induced into the part to get to your finished form. Some of the applications we've been involved in include industrial shocks, where we're retaining a cap on the end of the tube, steering column tubes, where after bearings pressed in, we're capturing as a secondary retention force, forming the lip over at the end of the tube. Ladder rungs, forming ladder rungs into sidewalls of a ladder. Fuel filter body assemblies. Something as small as a hearing aid battery, where we're putting the body to the cap. That's about as small as your pinky finger. Solenoid assemblies, where we're coming down and forming the lip over to retain the cap. Spark plugs, suction cup piston assemblies, semi-truck brake boosters. Those are about 8 to 10 inches in diameter. That's a pretty large hit that normally is around anywhere between 3,000 and 4,000 pounds to form the lip, about a millimeter and a half lip steel. And then semi-truck thermostat assemblies. Our second application type is cast housing end crimp, where we get involved in a lot of castings. A380 aluminum is an often used casting that we get involved in. Bronze, cast steel. There's a couple grades of magnesium that we've been successful with, and also we've had a couple applications where we've been involved in forming powdered metal. The biggest thing with the more brittle materials is based on volume, you don't want to move it very far, even at a low force induced into it. Hydraulic valves, gerotor pump assemblies, which are vacuum pumps for rear differentials in your drivetrain of your automobile. Upper strut mount or shock mount assemblies. Wheel hub bearings, small engine connecting rods, rear axle hubs covers, where Jake mentioned earlier, to come down and form to secure a sight glass without breaking it. power steering pump housings, and also electric motor housings for clutch fans. Undercut forming is our third. This is where we're using our articulating roller form. Pressure pad comes down, coming in and forming an edge or an undercut or an O-ring. Transmission carrier oil dam assemblies we've been very successful with. Ammunition projectiles, securing the end cap or the diffuser for ammunition. Overhead cam valve assemblies. Industrial sensors. Medical ball joint assemblies where we're securing the ball but still allowing it to freely move within the joint. Slipper valve assemblies and also speed sensor assemblies. Our fourth type is groove displacement, again using our articulating roller forming. And that's where we're doing O-ring grooves or undercut as shown here with this speed sensor, overhead cam valve assemblies, safety airbag initiator housings where we're securing or trapping the diffuser cap, and also suction cup piston assemblies where we're creating an O-ring groove. What's nice about doing this in a tube is when you're coming in and creating that O-ring groove, you can create a 360-degree lip so that if you're pressing a bearing or pressing any type of cap or whatever, that lip acts as that position where you want that to not go further down in your press position. And then of course, with some of them like in airbags and also in steering columns where we're trapping something, we're using our static roller forming to crimp over the top, and so now you got it trapped top and bottom. And our final application category is flaring. And you've seen this coming down in the center with vertical rollers and flaring out copper tubes. Pipe ends, refrigeration tubes, vibration mounts, and also in the semi-truck industry we've been very successful with using the flaring out process of putting together truck wheel oil hub seals.
So to review what we talked about, we talked about what Orbitform's roller forming process is, why roller forming might be a viable process solution for you, what the two types of roller forming processes are, articulating and static, what roller forming machine options are available, and then Brian went over what typical applications, and hopefully one of those resonated with you with something that you're familiar with. So for a live demonstration, you guys can come over to booth 505. We have both of these on our show loop there. We also can show you any of our other processes as well as our conveyor offerings and our assembly solutions other than roller forming. But thank you for your time.
Yeah. As Jim mentioned at the beginning of the presentation, our presentation's being videoed. We're also going to put it on our website. So if you ever want to access it in the future, come to Orbitform's website, orbitform.com. We also, in your presentation at the very back, you'll see a voucher, one of the last sheets. We welcome the opportunity for any of you to contact us or engage with us in a lab development and testing opportunity to take a look at your part or assembly and determine if roller forming or any of our other processes are a good solution for you, basically either if you got a new program or if you're looking at replacing an existing process, okay? Also in your packet, in the envelope in the very back, is a card. Please take that card to our booth, and we got a gift care package for each one of you. We appreciate your time coming here and investing. Know it's a lot of stuff to see, but again, we appreciate you wanting to be here and listen to us today. At this time, we'll field any questions that you may have. Okay. Hopefully we answered them all then.
Yeah.
Okay, awesome. Thanks everybody and have a great rest of the show. Appreciate it.